My name is Jamie Weaver, and I'm a part-time DPhil student at N-Dorms based at the Botner, although I'm physically located in Toronto. I also work full-time in the PharmEpi group in the Global Epidemiology Organization at Janssen Research and Development. This work is titled Quantitative Bias Analysis for Outcome Phenotype Error Correction in Comparative Effect Estimation in Empirical and Synthetic Evaluation. And the content of what I'm about to present relies heavily on the strong support from my collaborator Dream Team, whose names you can see here. Observational databases are increasingly used for estimating causal effects of drug exposures on clinical outcomes. The practice is encouraged by regulatory authorities provided care is taken to avoid known limitations of analyzing routinely collected data. One such limitation is that the data available often don't allow for accurate identification of patients with a certain clinical outcome. We use phenotype algorithms to identify patients who meet criteria for a particular condition, but our algorithms can only query patients based on what's available in the observational dataset. This discrepancy between a phenotype algorithm and the true clinical condition manifests as error in our analyses. We either miss patients we'd like to include, or we include patients that we'd rather not, and these inaccuracies can bias our results. Quantitative bias analysis, or QBA, is a method that incorporates outcome phenotype errors into causal effect estimates, but the extent to which it minimizes bias is unclear. This is the basis for our QBA evaluation that I'm going to speak about now. Our objectives were twofold. In the empirical evaluation, we assessed QBA in several PharmEpi comparative effect estimation scenarios that we replicated from a real study using real data. In the synthetic evaluation, we assessed QBA in an analytic space we defined by 3 inputs required for performing a QBA analysis to determine the method's operating characteristics in a large hypothetical space. A necessary input for QBA is the phenotype errors for the outcome in question, and these are non-trivial to obtain accurately or even at all. Yet, QBA performance depends on their availability and their accuracy. To illustrate, say a study produces the following 2x2 table with a relative risk of 2, and further, say a validation study samples and confirms as true positives 9 out of 10 target exposure cases and 8 out of 10 comparator exposure cases, which gives a target PPV of 90% and a comparator PPV of 80%. An intuitive QBA approach is to multiply target and comparator case counts by these error metrics, which simply rearranges the contingency table distribution, recomputing the relative risk now shows a corrected estimate of 2.25. But a main problem of these types of algebraic table rearrangement equations is that certain input combinations can produce negative corrected event cell counts, and this can invalidate the results. As I said, the algebraic adjustment changes person counts in the exposure outcome contingency tables based on the magnitude of misclassification. The equations that use sensitivity and specificity phenotype errors are shown here. The adjusted counts in the lower table are used to calculate the corrected effect estimates and uncertainty intervals. We used a novel validation method to obtain the phenotype sensitivity and specificity metrics for our empirical evaluation. A strength of this approach is that it facilitates rapid, large-scale, multi-database, temporal, and study population-specific phenotype error ascertainment, and this avoids the issue of using phenotype errors obtained in an external validation study from another database containing different patients from a different underlying population at a different time. So, in our empirical evaluation, we replicated an active comparator new user cohort study that estimated the risk of ischemic stroke among patients with hypertension. We compared the risk between ACE versus ARB and ACE versus thiazide-like diuretics during 1 and 2 year time at risk intervals. Before conducting the cohort study, we calculated ischemic stroke measurement errors that were exposure agnostic, which are known as non-differential errors, and those among patients in the exposure populations, which are known as differential errors. We then conducted our analysis under 6 different variants, 2 of which we didn't apply QBA, 2 that applied non-differential QBA correction, and 2 that applied differential QBA correction. We executed these analyses across 4 U.S. administrative claims databases and 1 U.S. electronic health record database. In total, we had 120 analyses. We assessed QBA performance with 3 metrics. The bias difference is the difference between the log of the QBA corrected estimate and the log of the uncorrected estimate. Relative bias is the percent difference between the QBA corrected estimate and the uncorrected estimate, and relative precision is the percentage change in the standard error of the estimate with and without QBA applied. These four forest plots report results for both exposure comparisons under 6 analysis variants and 2 databases. The analysis variant names suffixed with QBA are where the method was applied. Applying non-differential QBA to unadjusted analyses slightly increased the magnitude of the odds ratio and confidence interval width for both comparisons in these databases, which suggests that the uncorrected results were biased towards the null. Results were similar in the propensity score matched analyses also. Lastly, we varied non-differential specificity values from those computed using pHevaluator and noted that small specificity changes had a large impact on estimate correction. Applying differential QBA to unadjusted and propensity score matched analyses more greatly increased the magnitude of the odds ratio and confidence interval width for both comparisons in the EHR database, suggesting that if the errors differ by exposure group, the resulting bias is greater than if the errors are equal across exposure groups. Note that in one of the databases, the input combination of observed incidence, uncorrected odds ratio, and sensitivity and specificity values we obtained with pHevaluator produced implausible corrected results. We observed the least bias reduction in comparing analyses where propensity score matching had already accounted for confounding bias. We saw the greatest bias reduction when comparing unadjusted estimates to those corrected for phenotype errors differential to exposure status where propensity score matching had not already accounted for confounding. Further, estimate precision decreased most where QBA correction was applied differentially by exposure. Lastly, we noted that the magnitude of QBA correction varied strongly across scenarios where specificity differences were very small. One of our empirical examples had similar outcome incidence and measurement errors to a well-conducted estimation study in the same database. Given the similarities between settings, it was encouraging to see the degree of bias correction was also similar. This suggests that the measurement errors we obtained quickly using pHevaluator were of similar accuracy to those obtained conventionally using resource-intensive manual chart-based adjudication. Our empirical evaluation demonstrated that bias reduction was greatest in higher incidence scenarios where the uncorrected estimates were larger, which is uncommon in many pharmacoepidemiology comparative effect estimation contexts. A main finding is that in common low incidence settings, the accuracy and precision of specificity is a key driver of QBA impact. Now, in our synthetic evaluation, we created a grid space of the required inputs to a QBA analysis to correct estimates for outcome phenotype error. The full grid space included all combinations of 5 incidence values, 6 uncorrected odds ratios, and 20 non-differential sensitivity and specificity values. This created 12,000 2x2 tables into which we inserted 1 million target and 1 million comparator exposures. For each incidence uncorrected odds ratio strata, we computed a distribution of QBA corrected effect estimates for all combinations of sensitivity and specificity, and we plotted the contours across the grid space. Like the empirical example, we assessed QBA performance by comparing estimates with no phenotype error, where sensitivity and specificity both equal 1, to the 50th percentile of the corrected distribution. Here's a visualization of the grid space. Rows represent the input incidences, columns represent the input uncorrected odds ratios. Each cell is its own sensitivity by specificity plot for a unique incidence by uncorrected odds ratio combination. Let's review the plot where the incidence is 10% and the uncorrected odds ratio is 1. In this scenario, we see a narrow range of specificity values on the y-axis, from 99 to 100%, and sensitivity on the x-axis ranges from 5 to 100%. In this strata, the maximum valid QBA adjustment to the uncorrected estimate is about 20%, where sensitivity is around 5% and specificity is greater than 99%. Now, we vary the input by increasing the uncorrected odds ratio to 4. In this scenario, we see a narrow range of specificity values on the y-axis from 99.6 to 100%. The maximum valid QBA adjustment is greater than 10% of the uncorrected estimate, provided sensitivity is around 5% and specificity is greater than 99.6%. Although mathematically valid, this is a highly implausible result. Next, let's vary the input by decreasing the outcome incidence from 1 in 10 to 1 in 1,000. Here, the range of specificity values on the y-axis is narrower still, from 99.9 to 100%. The maximum valid QBA adjustment to the uncorrected estimate is 16%, where sensitivity is around 5% and specificity is greater than 99.9%. The main finding is that very small specificity changes have considerable impact on correction, but sensitivity has little impact. As we move down and right across the grid, we increase the uncorrected odds ratio and decrease the incidence input, and we see a similar pattern. The range of specificity values needed for valid and plausible results gets progressively smaller. Very small and precise specificity changes considerably inflates the magnitude of correction. Sensitivity progressively exerts less impact as uncorrected odds ratio increases and incidence decreases. To summarize, we identified the analytic space where QBA for outcome misclassification correction is implausible or invalid, and much of this space corresponds to common pharmacoepidemiology comparative effect estimation scenarios. Correction with imprecise specificity is problematic because small specificity changes can make implausibly large effect estimate adjustments. And impact of sensitivity on correction is pretty limited to where incidence is less than 1 in 100. The implications of this are widespread. A relevant example concerns COVID-19 vaccine safety research, where we've learned from recent Odyssey network studies that many important COVID AESIs, including thrombosis with thrombocytopenia, are rare, and their very heterogeneous incidence across diverse data sources could be attributable, at least in part, to variable measurement errors across sources. So in conclusion, chart abstraction validation methods are pretty much unable to obtain specificity values at the necessary precision to appropriately correct rare outcome estimates using QBA without an intractably large number of cases. A possible path forward includes the continued development and broader adoption of precise measurement error estimation methods, such as large-scale validation using a probabilistic reference standard, such as pHevaluator. Thank you.